Okay, so let's get started, so I don't have to keep you here all night. What did we do last week? We were talking a little bit. What did we do last week? Double integrals over regions. So we did type 1 and type 2 stuff. Cool. Okay, so today we're going to continue that trend of learning how to sum up a bunch of prisms in order to make an integral. Except this week we're going to do it all in polar, whereas last week we did it all in rectangular. And you'll see that it's not actually going to change that much. Okay, so the easiest region to define in our Cartesian plane is a rectangle, right? You just have to give me 2 endpoints, and 2 endpoints will define this region. Recall that I said that our notation here would say was a rectangle is given by 2 intervals. So it's given by an interval for which your x values can be taken and an interval from which your y value can be taken. So this rectangle are all the points x, y, such that x is in AB and y is in CD, right? And we also know that to integrate over this is quite easy as well. We want to take the integral from a to b of it dx and the integral from c to d dy, right? So the name of the game this week will be trying to make things look like rectangles, because we can integrate rectangles, or we can integrate over rectangles quite easily. What is the easiest region to define in the polar plane? Not a circle. What's the second easiest region then to define? Yeah, an arc, right? We're able to change r, which is the length of, which is the length. We can change the length of our, if we want to construct a circle, we can change our radius, and we can also change our angle. So if you move the r a bit and the angle a bit, we're going to sweep out something called an annulus, whose plural is annuluses or annuli. So I don't know, I think annulus is a funny word, but so if I snicker to myself, I'll lecture, you'll know why. Okay, so this is what an annulus looks like, and this is basically what a rectangle looks like in polar. Why? Well, because it is also defined by 2 endpoints. You give me an initial length and an initial angle, and a final length and a final angle, and it's going to sweep out this region. Right, so these are all points with length between r1 and r2, and with angle between theta 1 and theta 2. Right? And this is a rectangle, at least for purposes of integrating. Right? It's going to be easy to integrate over regions like this. So although it doesn't look like a rectangle, I could stretch this a bit so that it did look like a rectangle. But the important properties are the ones that are algebraic. Okay, so the rectangular region in the polar plane given by this rectangle. I'm gonna write rectangles the same way, right? I want to give you 2 intervals, and I'm going to take the Cartesian product of those 2 intervals. So the rectangle given by the region, r is between 1 and 2, and theta is between pi over 8 and 3 pi over 8, is explicitly equal to this set. So all points are theta, such that r is in between 1 and 2, inclusive, and theta is in between pi over 8, 3 pi over 8, inclusive. Here's your Cartesian grid, and we're sweeping out what? We're sweeping out a region from pi 8 to 3 pi over 8, which is from here to here, and we're allowed to move from 1 to 2. So here's 1, here's 2. Oh, geez, did I do that? I think I did this at 3. 1, 2. This region's wrong. This should be in here. So I could correct this by changing this to 2, 3. This is 1, 2, 3. So close but no cigar. All right, consider the figure below. I've labeled it in Cartesian. Is it a polar rectangle? What are the endpoints? 0 and 2? You have to give me 2 points in polar. But 0, 2, that's a good start. We know that the r's are going to be in the interval 0 to 2. So now all we have to do is figure out what the theta interval is going to be. What possible values of theta are allowable here? 0 to 2 pi. So the rectangular region is given by what? 0 through r by 0 through 2 pi. Right? And here you go. This is it in the region up to 2. But this is a rectangle for all intents and purposes. Basically, a rectangle is going to be the thing that is most easily describable in your coordinate system. Okay. So, let's play the same game that we played last week. Remember how we wanted to take the volume that was bounded by some curve, and we did this by dividing an area in R2 into little rectangles and taking sample points from within them. After we did this, then we constructed a bunch of prisms, added the volumes of the prisms, and developed a way to make these prisms small enough so that in the limit, the sum of those prisms gave us the integral. We're going to play the exact same game now, except instead of having a base that's a rectangle in Cartesian, we're going to have a base that's a rectangle in polar. Right? Or I'm going to keep saying annuli just so we don't get confused. Okay, so here is one region in polar, described by 2 points, a rectangular region. This is what happens when I divide it into 3 by 2 regions. So I'm going to divide the R region into 3 pieces and the theta region into 2. Right, so we have 1, 2, 3, 4, 5, 6. And again, I don't care where in this annulus that the point goes. A lot of textbooks will go through the technical detail, but it's not that useful, right? Again, the game is divide this into quote-unquote equal pieces, even though they're not really equal in this case, and just drop a sample point into each of them. And this is how I'm going to number them. Right, so this is R1, R2, R3, and this is theta 1, theta 2, right? So this is in R2, theta 1. If I divide more, so this is dividing R into 6 pieces and and theta into 4, this is now going to be in the 1, 2, 3, 4th position, theta 1. I can do another subdivision. This time it's going to be 7 ways up, 3 angles over, and I hope you see the pattern here. All right, so we need to now form our volumes, which means that we need to take our sample point, give it to our function to get a height, and then multiply by the area of the base. So what is the base in this case? Well, it's an annulus. So what is the area of the annulus? Surprisingly easy, but it took me like 5 minutes. Okay, I'll walk you through the solution. What's the area of this? Wrong. All of you just yelled out the equation for the area of a circle, pi r squared. There's no r. So try again. Pi r2 squared. Again. What's the area of that wedge then? Well, if the area of the whole circle is pi r squared, what's the area of the wedge? It's going to be some proportion of the whole circle, right? Well, if theta 2 minus theta 1 was pi, half the circle, how much of the area would it be? It's easier than that, right? Suppose I cut the circle in half. What would the area of half the circle be? Pi r squared half, right? If I gave you a quarter of the circle, it would be pi r squared quarter. The point is that we're taking a proportion. So what proportion of the entire area are we taking? Theta 2 minus theta 1 over 2 pi. Right? If we took 180 degrees out of 360 degrees, that's half. Right? If we're taking 10 degrees out of 360 degrees, that's 1/36. If I put out this wedge, right, which is theta 2 minus theta 1, then that angle over 2 pi is the proportion of the total area. So we get this. Theta 2 minus theta 1 half r2 squared gives you the area of this wedge. Who's paying attention? What's the area of this wedge? Just remember that it's a proportion of the area given by the complete circle. I think I labeled this. Oh, no, this is right. Well, what is the angle here in this wedge? If this one is at theta 1 and this one's at theta 2. Theta 2 minus theta 1 over 2 pi is the ratio of the area that we need. And in this case, the radius is r1. Right? So it's theta 2 minus theta 1 over 2 pi, pi r1 squared. can also simplify to theta 2 minus theta 1 half r1 squared. Okay. What is the area of this then, the original analysis for which we were doing this sum? Answers on the board. Well, we take the area of the whole wedge, the whole pink thing, or magenta thing, and then we subtract the area of the blue or cyan wedge. And that's exactly what I'm doing here. And we can simplify this to this. Theta 2 minus theta 1 over 2, r2 squared minus r1 squared is the area of that analysis. So just keep that in mind for when we're moving forward, right? Because again, we're going to have to take the area of this analysis and multiply it by height in order to get a volume. Here's a proof for a proposition that I will list after the proof, because I want to show you how this is really being constructed rather than us just introduce something magical. Okay, so consider that I'm giving you up here, this is the equation for the area of the analysis. And I'm just going to rewrite it, right? r2 squared minus r1 squared is a difference of squares. So this factors to r2 minus 1 times r2 plus 1. And then I'm just moving the half out here. Right, so this expands into this. But what do we know about r2 plus r1 half and a sample point? Well, r2 plus r1 half is exactly in the middle of this interval, right? It's the average of the two values. But ultimately, when we take our sample point from the analysis, it's going to have a value in between r1 and r2. It's basically what we're saying is that the difference between this number up here and our sample point is negligible, right? Since these regions are getting so tiny, we can just swap out the midpoint of the region with an arbitrary point in the region and take that for the area. Right? So thereby the area of this analysis is exactly equal to this, but approximately equal to this, but replacing the midpoint with a sample point. Right? So r Klein, r2 minus r1, theta 2 minus theta 1. Right? And this approximation tends to exact as the region gets closer and closer, but as the region gets more narrow. So what does this mean? Well, this means that if you take a sample point from within r1, r2, and we let delta r equal r2 minus r1 as usual, and delta theta equal to theta 2 minus theta 1 as usual, then I can write the area of one of these analyses as r Klein delta r delta theta. Okay, this is going to be important for when we try to integrate. Why? Well, to estimate the double integral of f, a polar function, or a function which takes a radius r and an angle theta, we need to sum the volumes of annuli-based prisms. Right? And I didn't want to draw this because these 3D plots take so long. We're hitting diminishing returns on these things. But you can imagine some analysts in the plane, and then you just stack these annuli on top of each other, and you get some sort of annuli-based prism. Right? Where again, it's just the base, the area for the base, which is r Klein, delta theta, delta r, times the height, and the height is going to be given by the value of the function at the point that you're working with. So the volume of the prism is going to be r Klein delta r delta theta times height. Right? And in order to form the integral, we just need to add a lot of these together. Right? Add the ones that are going to be in our integrating region. Okay, so here's an alternate proof before we move on about how we can take the areas of these annuli. So here's our setup. So we need to know what the area of dA is going to be. But we can remember that we're taking these intervals very, very, very small. Okay. This region here is r d theta. Because if we do the same thing that we did with the area, instead for the circumference of a circle, the circumference of a circle at some sort of theta wedge is going to be r d theta. It's this proportion, d theta over 2 pi times 2 pi r. The point is, if all these values get tiny, extremely tiny, everything looks straight. And this is something that I was talking about maybe the first lecture that I was teaching you guys. That the point of calculus is looking at curves very, very closely, and when we look at curves very, very closely, everything looks straight, including this analysis, in fact. So if this analysis loses all curvature, if the annulus is small enough, then how can we find its area? Well, how do you take the area of a rectangle? You could, but we know what the area of a rectangle is. Base times height, right? So the base here is r d theta, and the height is dr. Right? So this is exactly what we calculated before, that the area is going to be r dr d theta when these values are small enough. And this is not too important to understand, but it is an alternate proof and how things are treated in analysis if you ever take an analysis class. Don't worry, I'm going to have a lot of examples to solidify all of this. All right, so finally, here's our definition of a polar double integral. So if we let g be a polar function, which takes a polar value and maps it to a real value, and assume further that r is divided into n by m many sub-analyli, and you take a sample point from each of those sub-analyli, then the double integral over this region is equal to the summed, this sum, as you take n and m to infinity. Right? Again, I'm just saying, divide your region into infinitely many tiny small sub-analyli and then add the volumes together. And in the end, you're going to find that this is equal to the integral of g r theta by dr. R1 goes to, let me try that again. We can integrate this region by integrating g r theta r, taking r from r1 to r2 and theta from theta 1 to theta 2. And basically, this is all we need right here. In order to integrate over a polar region, we can do this, provided that the region is a rectangular polar region. Here's a proposition. If f is a function, a real function, that's given in Cartesian, that is continuous, as it has no breaks, and it has no points where it jumps to infinity, on the polar rectangle, AB through alpha through beta, then the double integral over this region of the Cartesian function, f, is equal to the double integral over the same region, but you can do a change of variables to polar. And so if you're given a function that's given in Cartesian, you can take that function and convert it to polar and integrate it to have the same integral. And again, this will all make more sense for concrete examples. So here's one. Here's a concrete example. Let D be this region. Right? X squared plus y squared is less than or equal to 4, which is the upper half of the circle. No, that's a lie. That's not the upper half of the circle. That's all of the circle. So how can I correct this? Any ideas? Because this collection of points would be the interior of the whole circle. So I just have to make the extra restraint that y has to be positive. In any case, the picture is what I want the region to be, so you don't have to pay attention to this too much. I guess if we bounded this from the other side by 0, we'd be okay. But anyways, how can I integrate over this region? What would your steps be if I just gave this to you right now? We already have enough information to do it. But what polar rectangular region is this? So what can our r range from? 0 to 2. And what can our thetas range from? 0 to pi. So the rectangular region is given by 0 to 2 cross 0 to pi. And knowing that, all we have to do is convert this function into polar and then integrate. So here we go. Here's the answer. Double integral over that region of 1 plus x squared plus y squared dA is equal to, from the proposition, taking r from 0 to 2 and theta from 0 to... Okay, now I really screwed something up, because that's 2 pi. Okay, so this should be the entire circle then. This is wrong. So you have to imagine the thing goes all the way around, so I'll amend what you said to 0 to 2 pi instead. I'll correct this, but this should be the whole circle. So we convert this to polar. And how do we do that? Well, x gets r cos theta, and y gets r sine theta. So if we plug those in, we get r squared sine squared theta plus r squared cos squared theta, which leaves us with r squared theta. And then I have to replace dA with r dr d theta. Don't forget to put this r in. That's a typical mistake. Okay, so what's next? This should be easy peasy now. What's the integral of 1 plus r squared by r? Oh, sorry, what's the integral of r plus r cubed by r? What's r squared on 2, r to the 4th on 4. Okay. Now we have to take, we have to evaluate this at top minus bottom. So that's 4 over 2 is 2, plus 16 over 4 is 4. So that's 6 minus 0, 6. And what's the integral of 60 theta? 6 theta. Oh, so I skipped that. Well, 6 theta from 0 to 2 pi is 2 pi times 6, which is 12 pi minus 0, which is 12. Right, so the name of the game here is just to look at the region that you want to integrate over, ask if it could be made into a rectangular polar region, and then switch your function from Cartesian to polar if necessary. Maybe I have another one. Cool. Let R be the region in the upper half plane, as in y is greater than or equal to 0, bounded by two circles, x squared plus y squared equals 1, and x squared plus y squared equals 4. Right, so we have one circle which of radius 1 and another of radius 2, and we're cutting the one of radius 2 out with the one that is radius 1. And evaluate the Cartesian function 3x plus 4y squared over this region. Okay, is this a rectangular region in polar? Yes. What can our r's go from? 1 to 2. What can our thetas go from? 0 to pi. Okay, so our rectangular region here is going to be 1 to 2 cross 0 to pi. So let's integrate this. So what's our first step? Well, this is given in rectangular. What do we want to work in instead? Polar. So we should convert this to polar. Oh. So x gets r cos theta, y gets r sine theta, and then we can put in our bounds. So we want to take r from 1 to 2, and not forgetting that I should put an r here when I replace dA, and I want to take theta from 0 to pi. What is the first integral? So if I distribute that r, if I distribute that r, I get 3r squared cos theta plus 4r cubed sine squared theta. I don't know how I integrated that. All right, this is easy once you realize that all the stuff with theta in it is constant. And so what's the integral of 3r squared cos theta? Well, because I have the document visualized now. Okay, this is important. This should be very quick. See what I have. And just holler at me if I get out of bounds. And it's going to distribute the r squared cos theta plus 4 cubed theta. We're in trouble if we can't integrate this quick. hope everyone knows that. Well, if we can't do single variable calculus, we're in trouble. Everything's going to get a lot harder. So I don't know if you're just tired tonight or... Okay. At least give me some fake nods and law. Because I don't want all of you lost in the whole class, because then that's just wasting all of our time. Okay, so to integrate this, yeah, this is just r cubed cos theta. Right? Because you just have to view cos theta as a constant. Knowing that, then, what's the integral of 4r cubed sine squared theta dr? Or to the fourth sine squared theta. Right? And then we have to take this from 1 to 2 and then integrate this. All right, so we're going to get what? 8 cos theta plus 6 sine squared theta minus cos theta minus sine squared theta. And integrate this until 5. So what do we get at the end? The integral 0, 5, 8 minus 1, 7 cos theta plus 15 sine squared theta. Okay, what's the integral of the first thing? The integral of this theta. Sine goes to cosine, 7 sine theta. What about this? I'm not looking for the answer necessarily, I'm asking for how you would do it. If you're on your homework and you're asked to integrate sine squared theta, how would you do it? Use the tables. This is obviously going to be in the sine to the end. If something looks easy that you think you should know the integral of, it's going to be in the integral tables, right? Sine squared cubed fourth to the there's literally sine to the n in here. Integrals, trigonometric forms, sine squared. That's the answer to how you would integrate that. You would cheat. You'd look it up. Because someone else did it. Right? But be lazy when you're taking these integrals. Right? Try to get your integral into a form so that you can look it up in the table. Right? There's a lot of strategy in just reducing something to a table lookup. So just keep that in mind. So I'm just going to finish this up. So table or a double angle formula would work in this case. I guess when I was doing this last night, I didn't have access to the tables. But I think you can print them out. Have you downloaded, or I shouldn't say downloaded, I should say obtained Stewart's calculus textbook yet? Go find this book. It's a very good book. And you should read and you should be practicing. If you really want to do well in this course, you need to be practicing. That's only if you really want to do well. Okay, so when we integrate the rest of this and actually evaluate at the bounds, we get 15 pi halves. Right? But the moral of the story here is you just have to find a rectangular region given in polar and change dA to r dr d theta. That should be all she wrote. This is very procedural. It's usually just difficult. The difficulty usually comes in actually finding a rectangular region in polar. Here's a question. So keep in mind that sometimes you can be given questions which aren't necessarily phrased, take the integral of this. Right? We'll give you a question for which integration is the key thing to use to get the answer. And whenever you hear the word volume or area, your mind should immediately go to, I need to take some type of integral. Right? Integrals or areas or higher dimensional areas are volume. So compute the volume of the hemisphere, that is the upper half of the sphere, where all the important countries are. No? When I first moved here, that was something that you guys do, which I find hilarious. Like, I'll be shown something, and be like, oh, this is the biggest lake in the southern hemisphere, or this is the best thing of this in the southern hemisphere. It's like, really? You got a lot of competition in the southern hemisphere? Rio really like, wait, is Rio even? Rio's underneath the hemisphere. Whatever. Compete with the northern hemisphere like the rest of us, and let's see how good you do. Hey, the American over there knows. The biologist shrinking in her chair. Okay, so let's take the volume of this hemisphere over the disk. Right? It could be more than the disk, but you'd get zero area outside anywhere else. Right? So just imagine the northern hemisphere, and I want to know what the volume given by this hemisphere. Who knows the answer already? Should be all of you. What's the volume of a sphere? 4/3 pi r cubed. So what's the volume of half a sphere? 4/6 pi r cubed. Whoa, wait. Half. 4/6, yeah, 2/3. Okay, so we know that the answer should be 2/3 pi a cubed. But just keep that in mind if we ask you a question that, if I'm like, oh, what's a quarter area of the circle, that you don't necessarily have to use integrating. In fact, I remember one of the last question on my calculus test was to take the integral of something that looked very complicated. But when you actually drew it out, it was the equation for a triangle, half a circle, and a square. Right? So those who realized that these were the shapes just had to go through and individually calculate the areas. Those who tried to integrate sort of algebraically were doomed. Right? So you have to use all of your tools in order to solve these questions. It doesn't, if you give me half of 4/3 pi r cubed here, I'd be obligated to give you full marks, 100 marks. Okay, so let's do this. So the problem now is that we need to look at our region here that we want to integrate over and convert it into a polar region, right? We're dealing with something circular, so it's going to be a polar substitution. So how can we can just work this out even without doing any math. So I want to integrate over the disk. So, and this disk has radius a. So what values can my r have? R can be taken from something to something in this disk. 0 to radius a. Almost there. 0 to a, right? The circle has radius a. I want to be able to move from the middle of the circle to the edge, right? So that's 0 through a. What can my angles be in a disk? New dance move. 0 to 2 pi. I know all of you know this. Just all humoring me. Okay, so we have our rectangular region. 0 through a by 0 through 2 pi. And now we can go ahead and convert the upper hemisphere to polar and then do our integration, right? So first we need to solve this for z, right? Because we only know how to integrate over functions, which means we have to isolate something. In order to integrate this with z squared included, we need a triple integral, which is next week. But we can take the upper half of the hemisphere easily, right? Because we can take the square root and take the positive part of it. If we wanted the bottom part of it, we take the negative one. But anyways, the upper half of the hemisphere is the equation z is equal to square root a squared minus a squared minus x squared minus y squared. That's just moving everything to the other side and taking the square root. We know that we're taking the upper half, so we can take the positive version of this. And also the interior of the radius a disk and polar is, as we said, 0 through a for the r's and 0 through 2 pi for the thetas. All right, so this is standard procedure yet again. Right? The first step, I'm going to convert the integrand, the square root a squared minus x squared minus y squared, into polar. And I'm going to replace d with our rectangular polar region. And I have to replace dA with what? R, dr, d theta. Just don't forget the r. The r is very, very important. So, what is x squared plus y squared in polar? R squared. Yes, r squared. Whoever said that gets 100 bonus points. Okay, 200. Okay, so I converted to polar. I changed my region here. The cos squared and sine squared, they cancel to 1. So now I'm left with the square root of a squared minus r squared r dr d theta. What's our strategy here now to integrate this? I actually forget the answer even though I wrote it last time. Well, two things can happen here, right? So first I'm looking at the square root of a squared minus r squared, and if that's taken to a half, if I take the derivative of that, chain rule is going to pop out 2r. Right? So that's where this r comes from. That probably would have been the smarter way of doing it, but you can also do this by parts. Right? So I look at this a squared minus r squared square root, and I think to myself, that's a basic form. There's no way that's not in the integral table somewhere. Now let's see. This isn't like that. These sheets actually come out. Oh, here's some square roots down here. I think it's this one. Yeah? Oh no, we have some squares, don't we? Yeah, we need a minus. Here. That's it, right? Oh no, we still need an r. Okay, well we can still use this for the integration by parts half that's not r, because r is going to be used to take the integral of this one. Point is I use the table and integration by parts in order to move from here to here. I'm not going to show you all the details because, well, single variable calculus should sort of be second nature to us at this point. And I am assuming you all aced single variable calculus, right? Oh yeah, y'all smashed it. I failed twice. Okay, so let's take this integral. And now we have to evaluate it at the top minus the bottom. So at the top, r gets a. So this is 2a squared minus a squared. That's 0. And the second thing is going to be evaluated at 0, which is going to give us a squared a over 3. Oh, sorry, a cubed over 3. And what's the integral of a cubed over 3? D theta. And so this is something you guys, I get a sense that you get confused by. Things, you have to view things as constants. If I asked you what the integral of 2 d theta was, you would all be able to answer that, hopefully, yes? What's the integral of 2 d theta? 2 theta. So if a is a constant, what's the integral of a d theta? A theta. So in this case, I'm taking the integral of a cubed by over 3, a constant, so who cares? So what's the integral of that constant d theta? The thing, right, a cubed over 3 times theta. And when I evaluate this at 2 pi and subtract it, evaluate it at 0, you get 2/3 pi a cubed. Right, that is correct. Right, and does this comport with what we hypothesized at the original outset of this question? Yes, it's 1/2 4/3 pi r cubed. Right, so we in fact confirmed what we were thinking. Okay, but you should go home and look over all of the slides again, because I sort of go a little bit quickly, and you may need some more time to go through these. But I try to give you enough questions from here so that you can at least do your web assign. So you don't have to look through the theory and stuff like that, but at least go and look through all the questions and answers, right? Because that will give you a good feel about how to do this. Okay, so here's another polar region. You don't like this one? It's the type of region that you'd get if a duck were walking across. But, okay, so you remember these type 1 and type 2 regions? These type 1 and type 2 regions in Cartesian meant that one of the two things had to be like a constant interval. Right? So you can say x goes from 1 to 2, and y goes from 0 to x. Because you pick an x first, and then you choose 1. Or we could have said y is in between two values, and then x is another value that depends on y. The point is that one of the two things needed to be known. We can have the same type of region in polar, where you give me two endpoints again, but you have to give me two functions. Right? You have to tell me, so here theta is going to be known. We're going to move from theta 1 to theta 2, and you need to give me two functions. So you need to tell me that if I move to some sort of theta in between here, where is my starting point on R and where is my end point on R? Right, so if I just cut a line through here at theta, exactly halfway between theta 1 and theta 2, I move from R1 theta to R2 theta. That theta is the thing that's known. Right, here at the beginning at theta 1, this function is going to say, well, you should be R1, right, this curve, at theta 1 out. And if I'm following theta along here at theta 2, R2 theta 2 gives us this other endpoint, right? So again, we know the angle that we're sweeping out, and we have two functions which can tell us from what our R can range from. We also know how to integrate over these regions. So this is called the four-leaf rose. It's an interesting shape. So find the area enclosed by one loop. Here's one loop. And I'm going to tell you that this loop is generated by moving from minus pi quarters to pi quarters, which is what? Minus 45 degrees to plus 45 degrees of the four-leaf rose. Right? And this four-leaf rose is given by the equation, polar equation, r is equal to cos 2 theta. Okay? So we need to find an area, which means that we should integrate something. And this is a polar function. So we're going to need to figure out what polar region, right? So we need to integrate this shape over something. So what should our over be? Okay, so I'm going to tell you that it's this type of region. So do we have a fixed known region for the thetas to sweep out? What is it? Minus pi quarters to pi quarters. Good. Okay, so one of the edges of our rectangles is known. What's the other thing that we need to know? For each theta, we need to know from what values our r is allowed to be. Consider, though, that we're always starting from the origin. We're going to start from the origin and move out. Right? That means one of our endpoints for r is going to be 0, right, in all cases. Right? So I'm going to say here, one of the functions, right, is just the constant function 0. We're always starting at 0 and moving to something. Now suppose I give you an angle in this interval. We move from 0 to what? How far out do we move if we're at theta? Cos 2 theta, right? Because that's the value of the function, right? The function is saying at any given theta, the distance is going to be given by cos 2 theta, right? So between when theta is in minus pi quarter to pi quarter, we have r is in 0 through cos 2 theta. So that's this rectangular region. We're going to go from 0 to cos 2 theta by minus pi quarters to pi quarters. Some of my colleagues may complain that I'm writing this, because you should never have something with unknowns here and knowns second, but whatever. We can be a little bit sloppy. We're not mathematicians, we're engineers. And physicists with spherical cows. Okay, so to find the bounded area, we have to integrate over the unit function. Why the unit function? Why aren't we integrating the curve we're given? Well, what are we trying to find? Yeah, of one closed loop. And so this is our region. This isn't defining a volume, like in space. So I want to go to each point in this region and count it once. One, right? I say, okay, here is an area by 1. Right? So if you have an area of a square, 4, suppose, and I make it height 1, what's the volume? 4. Right? So if you have a unit prism or unit height prism, the volume of the prism is just going to be given by the area. Right? So the volume of this prism, so if I took an integral over this region and just put 1 up top, that volume is going to be equivalent to the area. And in the same way that all prisms are equal to the area if they're of unit height. So I'm going to say, find the area of this curve at height 1, or find the volume that this curve is bounding at height 1. Right? And that's going to just give you the volume of the area in question. All right, so double integrate this over 1. Let's put in our bounds. Right, so I want to go from 0 to cos 2 theta, and from minus pi quarter to pi quarter. And remember that the integrands and these dRs have to match, right? So this is saying integrate from minus pi quarter to pi quarter on theta, and this is saying integrate from 0 to cos 2 theta on r. Right? So even though there's a theta in here, it's still referring to the r. Okay, so what's the integral of r dr? R squared half. So r squared half, evaluated at cos 2 theta minus 0, gives you cos squared 2 theta half. Squared 2 theta. Did I miss a half? Am I missing a 2? Yeah, I think I may be missing this half. Okay, so my answer will be off by half. Just keep that in mind. What is the integral of cos squared 2 theta d theta? Table lookup. Either table lookup or double angle formula. What did I say? Double angle formula. Right, so I can change cos squared 2 theta to 1 plus cos 4 theta. And after doing this, I can integrate cos 4 theta very easily to minus sine 4 theta quarter. Now plus sine 4 theta quarter. And then when I evaluate that, a pi quarter to minus pi quarters, we get pi over 8. Because sine at any multiple of pi is 0. Right? So the first one is going to be pi plus 0, and the second one is going to be, the first one's going to be pi quarters plus 0 minus pi quarters plus 0, which is pi 16ths half pi 8. Okay. Here's another one that's a little bit difficult. So let D be the region inside the circle, this circle, x squared plus y minus 1 squared equals 1. So remember, this is this unit circle whose center has been moved up 1, right? So 0, 1. Bounded below by the line y equals x. So here's y equals x. So I want to integrate x over this d. Okay, so how do we start? What have we been doing the whole class? I can't hear you. Convert to polar. Okay, that one's easy. So x in polar is r cos theta. So we're going to be taking the double integral over r cos theta, but we need a rectangular polar region, do we not? So what is our rectangular polar region? What do we need to know? We need to know what values of theta are allowed, and what values, and for each theta, how we have to move our r. So what thetas are allowed here? Well, here's 0. Are we in the circle? No, here's 3 pi over 2. I don't think we're in the circle. Let's worry about where we have to start then. Pi on 4. Can everyone see why? So this is a line with slope 1. So if you imagine this is a triangle, 1, 1, what's the angle in here? Pi on quarter, right? This is a 1, 1, 1 triangle. So the first angle that we can go to is pi on quarter. And what's the last angle that we can go to? Well, here's pi half. No, this is pi half. Right? Here's 3 pi half. Any ideas? Pi. We can go from pi quarters to pi. So, when theta is in that region, how far can our r go? Maybe I should move to this one. Well, again, the answer's on the bottom. I forgot to pause it out. But we should understand the answer. Yeah? Okay, so first of all, this circle was given in Cartesian, x squared plus y squared minus 2y. Let's convert it to polar. If we convert to polar, we get r squared sine squared theta plus r squared cos squared theta minus 2 cos theta is 0, where the sine squared and cos squared cancel in some sense. So we're left with r squared. Can I get rid of the r squared? There be a square here. Does that stir everything up? This may have to be root 2 sine theta. So r sine squared theta plus r squared cos squared theta gives me r squared, which means r squared is equal to 2 cos theta. Okay, so I am missing a square. Here. So what do I have to substitute for x and y in order to convert to polar? Did I screw that up as well? Yeah, I think I really screwed up this question. Okay, so let's try working it out. This gives me r squared equal to 2r sine theta, which gives me r is equal to 2. Okay, it's not as severe as I thought. That sine theta should just be cos theta. See, even professors make mistakes, since we don't get penalized. You guys do. Okay, but we should be able to correct this. I think if I replace that 2y with the 2x, that's just the circle shifted left one. Well, okay, maybe we should continue and just figure this out. Okay, so then if I have circle, this is at 2 and 1. We also have all the points in that circle given from? Yeah. It's a hook function, right? You give it a theta. You say, I'm going to turn this much. And it's going to say, okay, then you have to go out like in the Cartesian plane, where you go out x and up some part in y. In polar, you rotate a bit and then go out. Right? And your function is telling you how much you go out. So again, you need to go from 0 to the edge of this circle, and the edge of this circle is given by 2 sine theta. Could we try integrating? Can't be worse than the wrong solution that I have written. So let's use what we know. We want to take the double integral over d of x, dA, which means that I want to integrate over what? So I want to integrate over r, dr, d theta. So r goes from what to what? Sine theta. And theta goes from what to what? Perfect. And what goes in here? Not x. R cos theta. Really, we are integrating 0 to 2 sine theta minus pi quarter to pi quarter of r squared cos theta dr d theta. Okay, first integral. What is the integral of r squared cos theta dr? R cubed on 3 cos theta, right? Because cos theta is a constant, so let's just treat it, just forget that it's there. So you get r cubed over 3 cos theta. We want to take this from 0 to 2 sine theta. And then we still have to integrate this afterwards. Great. Okay. So top minus bottom here, well, we love zeros, so the thing on the bottom is going to be 0. The thing on the top is going to be what? Well, it's 2 sine theta cubed by thirds. So that's going to be 2 cubed, which is 8. Sine cubed theta cos theta over 3 theta. Do that? Sorry? Oh, you're right. Why am I going? Yes, sorry, this was the original. Okay, which one's wrong? Here? All of this is wrong, isn't it? Yeah, it's pi on 4 to pi. Sorry. I'm doing the previous example in my head. Oh, boy. Okay, now what? What do lazy mathematicians do at this point? Trigonometric forms. So what are we looking for? Sine to the n cos theta. Do we have something like that? This. Yeah? I don't have my glasses on. That's visible to you guys? Alright, but you see how you could use this to solve this? Right? This is sine n cos m, but the cos is 1. Right? So, might as well do this to show you how to use this. This one, which the form's not that easy, so we have, how much of this can you see? Not a very. This one I'm using, so this is equal to minus sine root theta cos squared theta n plus m, which is 4, plus n minus 1, which is 2, 4, minus and then you just have to repeat it, right? But the point is, try and find these tables. You could even ask Wolfram Alpha. Let's do that right now, actually. What's up? You have to ask Bjorn about that. I was given tables for my exam. Or they would at least say, do this integral. Here you may want to use this, I don't know, you may want to use this integral when you're doing this integral. But again, like when you're doing your homework and stuff, don't waste that much time. So do you guys know what Wolfram Alpha is? Have you guys used it? Okay. Well, good. You should. Like, cheat on your homework. Like, I don't want. Let me show you how to do this. Wolfram Alpha. So let's just ask the system to solve this integral for us. Oh boy. Finish. What is the integral from pi quarter to pi of sine cubed theta times cos theta d theta? There you go. Minus 1/16. Right, so that would be that's the answer here. It's minus 1/16. Sorry, I kind of screwed that up. I'll fix it. I really screwed everything. Which means, though, if you do it on an exam, I'm going to be more kind. I'm not going to say you are wrong from here on in. Probably. What's right and what's wrong? This is wrong? Yeah, and I also missed an R here. Anyways, I'll fix it. There you go, table lookup. It was easier when I didn't have a cos, because then I got signed to the 4. That's obviously table lookup, but anyways. All right, 45 minutes. Let's see how much of this we can get through. So, converting to polar and spherical and ultimately cylindrical, which we're going to do next week. We do this because it makes integrating easier. If I asked you to do all these questions again, but in rectangular, you basically have to do 4 integrals each time. Right? Because the most that you can represent as a function is an upper hemisphere or a bottom hemisphere. And instead of taking your r from 0 to 2, you have to take it from 0 to square root x and 0 to square root y. A circle is a lot more difficult to represent in rectangular, right? But we don't want to have to go through this whole lecture every time we introduce a different type of change of coordinates. Right? We want to ask, what does it mean to do an arbitrary change of coordinates? And then given this change of coordinates, how can I then integrate in that coordinate system? All right, so consider converting from rectangular to polar. This is something that we call the change of variables. Right? And generally, this is called the transformation of your coordinate system. Right? So you give me R2, and I convert it or transform it into polar. Right? So you give me the whole real plane, and I convert it into a system which takes reals and angles between 0 and 2 pi. Right? So this says this is a symbol that means maps to. Right? R2. This means maps to. So R2 goes to r by 0 to 2 pi, so from the real plane to polar. And xy, that pair xy, maps to the pair square root x squared plus y squared arctan y. And this was our two-polar conversion from Cartesian conversion. You give me a real point on the real plane, I'll give you its equivalent representation in polar. You've already seen performing the transformation can help make integrals easier. Let's investigate what other transforms are possible. Okay, so generically, there's something more general than a function. If a function is just a collection of points that have to pass a vertical line test, or a horizontal line test, then let's just say any collection of points, right, pairs, is called a relation. right? So the function for a parabola is a relation. It relates 1 to 1, 2 to 4, 4 to 16, right? So in some sense, 4 is related to 16. The image of a relation is all the things in the second component, right? So in functional talk, the image is the range, right? So if I, again, use this parabola example over the reals, the transformation, the image under that transformation are going to be all positive reals, right? Because that's the range of that function. So we can consider this t to be the range over the domain given by A. T is 1 to 1 when you map a point and you map a different point and they end up in the same place. And that is not allowed, right? So if A1 and A2 map to the same thing, then A1 and A2 have to be the same thing. That's the definition of being 1 to 1. If you want to think of this as functions, they have to pass both the horizontal and the vertical line test. The important thing about these 1 to 1 relations is that you can invert them. They're very easy to invert. You just take each pair and you swap it. Right? That's how you invert a relation. So note, if T takes A to B, then this is if and only if T inverse takes B to A. Right? So you can go from A to B by T, and then back from B to A by the inverse of T. So just see these relations as relating one element from one set with another element from another set. So I'll omit the proof, although it's not that hard. See if you're paying attention. Take square root x, right, over the positive reals. Is this a 1-to-1 function? Yes, it does pass the vertical and horizontal line test. So what's its inverse function? What squared? So if we know that t of 4 goes to 2, then t inverse of 2 has to go to 1, which is what? 2 squared. Right, so I'll say it in general. If we know that t of a goes to square root a, then we know that t of square root a has to go to a. And if t of 2 goes to 4, then t inverse of 4 has to go to... No. If t of 4 goes to 2, then t inverse of 2 has to go to 4. If t of 9 goes to 3, which it does, then t inverse of 3 has to go to 9. So the inverse function here is you give me a y point and you just square. Right? That's the thing that you get. Right? Because t of y squared gives you 1. Okay. Let t be the parabola now. Is t 1 to 1? Does it pass the vertical line test? Pass the horizontal line test? Okay, so prove it. Prove that this isn't 1 to 1. How would you do that? You have to show that it fails the horizontal line test. Well, how do you show that? No. That's a good start, but that's not proof. Okay, give me 2. 1 and minus 1, right? T of 1 goes to 1. T of minus 1 goes to 1. But minus 1 and 1 aren't equal, right? And for t to be 1 to 1, this had to be true for all points, right? So no, you picked a good one. I like the one that you picked, right? So no, t1 is equal to t of negative 1, and they're not the same, right? This one point would invert to 2 things in its domain, so that's not okay. But again, just think, it has to pass the horizontal and vertical line test. That doesn't suffice as a proof, but it will certainly allow you to answer yes or no to something being 1 to 1. Okay, why am I telling you this? Well, you can transform anything, right? So to give me 2 sets, I don't care what's in them. You can transform pairs of something into the real plane, right? as long as this transformation is one-to-one. Right? Something that you want to transform from something to R2, so you need to take 1 point from here and associate it with exactly 1 point from here, so that I can reverse it. Just imagine tying pieces of string from one element to here. Right? And all of these pieces of strings can only have 2 things attached to them. Here's some notation. So we're going to have a transformation T, which takes something from like polar, for example, and converts it into Cartesian. And when this is the case, we're going to individually refer to x and y as 2 functions. So this is a little bit of confusing notation, but it will be helpful. Right, so when T is a transformation on u and v, and it gives you x and y, then we can say x and y are both individually functions themselves. Right? So you give me a u and v, I can give you x, I can give you a u and v, and you can give me a y. Right, so that T applied to u, v is the pair where x gives you a function, x gives you a value based on u and v, and y gives you a value based on u and v. All right, so as a concrete example, because I know this sort of general stuff is confusing, the transformation for converting from polar into R2 is given by this transformation. Right? You have to give me a pair comprised of a real number and an angle, and I map this real value and an angle to r cos theta, r sine theta. That gives us our transformation from polar into Cartesian. To take the inverse transform, that is to go from R2, Cartesian, into polar, you give me an xy in rectangular, and I give you back the square root of x squared plus y squared, arctan y over x. So for any transformation, we should be able to tell what the forward transformation is and recover the inverse transform, which in both of those things are important. Right, but soak up this a little bit, because this needs to make sense in your mind before we continue. Any questions before I move on? Right, so whenever you see T and T inverse, in your mind you can think polar if you want. Everything that I said, everything that I'm going to say should make sense as well for polar. But again, we're scrapping this notion that we're dealing with a specific transformation and just doing generic ones, right? So as long as you're moving 1 point to a unique other point, we should be fine. Okay, I'm going to give you a transformation, and I'm going to take it from a rectangle, right, 0, 1 by 0, 1, to R2. And I'm going to give it by this mapping. Right? So you give me a point from inside your square, and you produce, whoops, where am I going? And you produce this pair as a result, u squared minus v squared 2uv. So let's investigate what the new region is going to look like. So remember, we're going from the uv plane to r squared, to what we usually call the xy plane. In the uv plane, this is the unit square that we drew. Right? So notice that we have 4 endpoints and 4 boundaries, right? S1, S2, S3, S4. What is the equation of this line here? This is the u-axis, this is the v-axis. What's this? V equals 0. Perfect. What about up here? V equals 1. And what's this? U equals 1 and u equals 0. Perfect. Right? So we know the exact locations of the endpoints. We know the equations for the boundary of this region. Now we're going to take each of those things and transform it to see what new shape is produced. Okay, so recalling that our transformation takes uv and maps it to u squared minus v squared to uv, we can map the endpoints to new endpoints, right? So we had the origin on uv. If we put that into here, you get 0, 0. So 0, 0 maps to 0, 0. If you took the point 1, 1, which was the northeast endpoint of that square, you get 1 minus 1 is 0, and 2 times 1 times 1 is 2. Here, if you put in 1, 0, you're going to get 1 minus 0 times 0. And here, if you plug in minus 0, 1, you're going to get 0 minus 1 and 0. Right? So these are where the endpoints of the square move to under that transformation. Okay. It's a little bit more sophisticated now. Now we have to deal with each of the lines, the boundaries of that square, and see how they transform. Well, as a set, as a collection of points, that line were all the points u naught such that u could go from 0 to 1. Right? We had 0, 0, 0.50, 1, 0, and all the points in between. Right? So this is the graph of that line on that integral. So what happens when I take that collection of points and send it through our transform? Well, we're going to have to take the transformation of u naught, right, of each of those points as u runs from 0 to 1. So what is tu0 equal to? What happens when I plug u in 0? What happens when I plug u equals u, v equals 0 into here? Isn't it u squared 0. u 0 goes to u squared minus 0, and 2 times u times 0. Right? Right, so we get a new collection of points, u squared 0, such that u goes from 0 to 1. Okay, but that's still just the region between 0 and 1. You square anything between 0 and 1, you actually get smaller if you square something in that region. A half squared is a quarter, it's smaller. But the biggest thing that you can get to is 1, and its square is still 1. Right, so taking all the points between 0 and 1 and squaring them just gives you all the points between 0 and 1 back again. Right, so the image of that line, 0 to 1, is just the line 0 to 1 again. So that one's kind of boring. This one will be more interesting. So here's that other line. Here's that vertical line at 1. Right? So you go to u equals 1, and you take all of the collection of points v from 0 to 1. That's this line. So we have to run each of those points through the transformation. So what now happens when I give this transformation 1v? Well, u gets 1, so that's 1 minus v squared, 2 times 1 times v. So that should give me 1 minus v squared 2v, as v goes through 0 to 1. But what's this? Well, note, if x is equal to 1 minus v squared, and y is equal to 2v, as this says, right, because now we're in the new coordinate system, then x is equal to 1 minus y squared over 4. Right? Because y here is, v is half of y, so I get x is equal to 1 minus y squared 4. So that's how I get that. Which means that the new collection of points can be written as x, 1 minus y squared over 4, as x goes from 0 to 1. And so here's the new graph. Right? So if we take the graph of the line from under the uv coordinate system, send it through the transformation, you get this collection of points now under the new transform, in the xy plane. Right? So here's our first one. Here's our second one. I can repeat the same thing again. It's just the other two lines, so I'm going to just go through it quickly because it's just symmetrical to the thing I showed, sort of running out of time. But that gives you this line here and this line here. Okay? So we've taken a rectangular region and transformed it into this popad, wherever you want to call it. But the idea is to do the opposite later on, right? You say, oh, I can turn this popad into a square, and I know how to integrate over squares easily. And so this will be the game. Being given a region and saying, okay, well, how can I change this into a square region, maybe, right? If your region is difficult to integrate over. You're going to have to look this over again because these transforming boundaries is difficult to conceptualize when you first start doing it. Here's how the complete region looks like after it's been transformed. So remember, S was the unit square given on the UV plane. And after it goes through TS, I can characterize it like this. Right? I have the endpoints minus 1, 0, 1, 0, 0, 2. There was a 0, 0 endpoint in here, but it's not really an endpoint. And we have these two curves here given by x equals 1 minus y squared over 4, and x equals y squared over 4 minus 1. So square converts to popad, and the inverse transform would take the popad to the square. I don't know why I like calling that popad. Maybe bishop. I think popsat needs to be higher. Okay, so we see how a change of variables affects a double integral. Right? The first half of this lecture was seeing how converting to polar changes things. And basically the game at all points is, how can you take your region and divide it into subregions so that I can go and take sample points and start constructing prisms? As long as I know how to take the area of the base of the prism, we are gravy. We can just do all the normal integrating stuff that we've developed before. So we consider our rectangular base, returning to this. In rectangular, we liked rectangular bases because we knew that the area of this rectangle is just going to be delta U, delta V. In polar, we knew that it's going to be R, dr, d theta. What's it going to be now for general transformations? Who knows? So suppose I took some square region and I transformed it, and now it looks like this blobby region. We don't necessarily know what it is. How can I calculate the area of this sort of unknown region, right? Because if we can do that, that means we can take the integral. Well, let's do this. Right? I can define a vector from this point here. So you need to at least know one endpoint of the region. So in this case, it's t. It's x naught, y naught. And if I draw a vector from here to another one of its endpoints, and here to another one of its endpoints, so in particular, I move down. I start at x naught, y naught, which is the transform of u and v, and I look where I get to if I take this v and I just bump it up by a tad, by delta v. So I just move a little bit here. And this one is where I end up if I just push that u by delta v. All right, so if I took the limit of this vector as it moved along here to this point, I would get the secant vector, and in the limit I would get the tangent. And the same is true for here. And so notice, along the u direction, that the partial derivative of t with respect to u is equal to the limit as delta u goes to 0, so as this point approaches this other point. And you just have to take the difference of this vector with this vector and divide by delta u. Right? That's the definition of the tangent. But however, if I can take this delta u from down here and I can multiply it out and remove the limit, and say delta u of the partial derivative of t over delta u is approximately equal to this difference. Right? Just look at this equation, knock off the limit, right? So this becomes an approximation rather than an equality, and then I just multiply through by delta u. The important part is that this point minus this point is equal to this. Why am I telling you that? Well, because now when I look at the tangents themselves, the length of those lines are given individually by delta u partial t over partial u, and delta v, and this length here is given by delta v over the partial derivative of t by the partial with respect to v. What is the area of this trapezoid? The cross product. Do we all remember that? You take two vectors and you find their perpendicular cross product. That cross product is actually giving you the area of the trapezoid. The area of the parallelogram is given by the length of the cross product. So I'm going to take the length of the cross product. Since delta u and delta v are constants, we can remove them from this cross product. And in the end, so this value here, this cross product of the partial derivative of t with respect to u and the partial derivative of t with respect to v times this is going to be the area of that blob, right? Or at least a good enough approximation of that area, because as this blob gets smaller and smaller and smaller, this parallelogram is going to be a better and better approximation of that blob. Right, so this means we just need to know, we don't need to know the area of the blob, we just need to know a position on that blob, its tangent directions, to obtain approximation of the area. So recall that when t of uv was the transformation which given u and v gives you an x and gives you a y. So if we actually compute the cross product of the partial t by u cross partial t by v, what do we get? Well, that's going to be, so do you remember how to do partials from, what was it, lecture 1, lecture 2? Anyway, so we need to take the partial derivative of x uv by du and the partial derivative of y uv by u. and cross that with the partial derivative of x uv by du and the partial derivative of y uv dv. And so why am I throwing in these extra zeros here? Yeah, I'll accept that as an answer. 50 bonus points. It's because the cross product is not a planar operation. Right? If you're working in R2 and you took the cross product, you get something sticking out. You're in R3. So you can really only take cross products of three-dimensional vectors. So I can just say, well, okay, just go into the third dimension, you have height 0. Right? But the resulting height is going to give you the area of that trapezoid. Which one? Oh, this one should be dv. Yeah, good call. Either this should be dv or this should be dv. Doesn't matter. It'll give you the same thing in the end. So the cross product is calculated by putting ijk across the, so doing a determinant of a matrix where you put ijk across the top. Delta x, delta u, delta y, delta u, that's this. I should say partial x, partial v, partial y, partial v, 0. So what's the partial derivative of x with respect to, oh, we don't have any yet. Okay, so I just cofactor expansion along this column, right, because I want to utilize these zeros. So it's going to be, so if I do the determinant here, it's going to be this position times the determinant of this, which is 0, plus this position times the determinant of that, which is 0, plus k times the determinant of this, which is exactly this value here. Okay, so this determinant, or this matrix that's in here, is very important. It's so important, actually, that it gets its own name. It's called the Jacobian of the transformation. And it's just defined to be exactly what it is we just calculated. Right, so when you see this partial xy over partial uv, a derivative of a function with respect to another function, this is its definition. Right? This is new notation that we are introducing that is defined to be this. So if you think to yourself, that doesn't make any sense, it does make sense because we defined it ourselves, right, to mean this. So just keep that in mind. So this is called the Jacobian. We're going to be using it a lot. And just observe here that we can just do the, if we take the determinant of this, we're going to get partial x partial u by partial y partial v minus partial y partial u minus partial x partial v. Example. Okay, so let's check our polar Jacobian. What are we going to get? Well, there's the definition of the Jacobian. I'm going to put in our x and y's, so let's see if we can take partial derivatives. So what's the partial derivative of r cos theta with respect to r? What's the partial derivative of r cos theta by r? Derivative. You gave integral. So derivative would be cos theta. What's the partial derivative of r sine theta with respect to r? Sine theta. Okay, so what's the partial derivative of r cos theta with respect to theta? R sine theta. How about this one? Minus r. Perfect. Cos theta, sine theta, minus r sine theta, r cos theta. And if I take the determinant of this, you get r cos squared theta plus r sine squared theta, which gives you r. Do you recognize that r? So what did we have to replace dA with when we converted to polar? R dr d theta. And that r from that conversion is actually the Jacobian. And so we'll develop that again, but that's where it comes from. And that r that everyone forgets is everyone's forgetting the Jacobian. Oh, what do I want to show here? So here I just want to say that now we know that the area over our region can be given by the Jacobian evaluated at a point times delta u delta v. What that means, essentially, is that if we want to take a double integral over some region R, which is, this is given in Cartesian, or this is given in R2, I can say that this is approximately equal to, definitionally, to the sums of all of these prisms, which we can convert, right? I can take xi, yi, instead assign that to a transformation, multiply by this Jacobian, and switch to delta u delta v. And that's going to give us the integral over a new region S over f of the transformation of those variables times the Jacobian. Right? So this is the proposition that you're going to need. Right? It doesn't really matter if you understand the proof or not, but if you're asked to integrate, double integrate over this region, and you want to do a transformation of variables, this is what you're going to need to do. Right? That if you can come up with some transformation t, you could swap out this dA for the Jacobian du dv, and do your general swap of variables, and also have to change the region. So if you're just imagining that you have some curve over a region in space, and you want to take that volume, that we now have the mathematics to stretch the thing on the bottom, and we know how the thing on top stretches accordingly. So again, if you wanted to take a circle and stretch it into a square, that's somehow what we're doing. Okay, so let's confirm this proposition for polar, which is given by a transformation with these components. And I think maybe this will be the last thing that we can do today. So if you give me a length and an angle, then I can give you an x. That's r cos theta. If you give me a length and an angle, I can give you a y. That's r sine theta. Our proposition says that to integrate over r of a Cartesian function fxy dx dy means that I have to find a transformation, right, that maps to r. So you have r, I want to have a transformation. It has a region which maps to it. I change x and y to r cos theta and r sine theta. I multiply by the Jacobian here, dr d theta. And we get integral, double integral over the inverse transformation of r, f of r cos theta, r sine theta, r dr d theta, which checks out with what we developed before. Okay, so you should be able now to answer, how much more do I got? Too much. Don't worry, this is not WebAssign homework till next week. So, your WebAssign homework this week is only polar stuff, but next week is going to be triple integration. So they wanted me to do triple integrals and this next week, and I think that would have been too much. So next week we'll finish this up and then do triple integrals. But maybe give this question a try. You should be able to answer this. So try to answer it knowing that you can then look up the solution. Right? So don't get too, yes? Midterm? I think anything up to the, what time's the, if we've taught it before the, when's your mid-semester? Okay, so my official answer is you have to ask Bjorn. He's the course coordinator. He's the one setting this up. But your mid-semester's next week? So not this, okay? Okay, when I say not this, I mean not the general transformation stuff. Know how to do, you should definitely know how to do these rectangular polar regions, these analyses, analyze. But yeah, give this a try when you go home, right? So it's just a matter of going through the stages. You won't really comprehend this until you practice a bit. So we'll do these two next week. I'll try to go through them slowly, but we're also going to talk about volumes, platonic solids, and triple integrals. So, and again, come visit me in my office if you need help, and especially if you have a midterm next week. I haven't seen, 0 people have come to come get help from me, which means that we can give you a very hard midterm, right? If you guys aren't coming for help, that means everything's too easy because you understand everything perfectly, is my assumption. Mm-hmm. Have you guys started studying yet? You can't study math at the last minute. You need to be doing like an hour of math a night, maybe. If you try to cram it all in next week, it won't work. That's the biology approach.